MIT researchers have designed low-cost photovoltaic-powered sensors on RFID tags that work in sunlight and dimmer indoor lighting and can transmit data for years before needing replacement. By 2025, experts estimate the number of Internet of Things devices, including sensors that gather real-time data about infrastructure and the environment, could rise to 75 billion worldwide. As it stands, however, those sensors require batteries that must be replaced frequently, which can be problematic for long-term monitoring. MIT researchers have designed photovoltaic powered sensors that could potentially transmit data for years before they need to be replaced. To do so, they mounted thin film perovskite cells as energy harvesters on inexpensive radio frequency identification (RFID) tags. Perovskite cells are known for their potential low cost, flexibility, and relative ease of fabrication. The cells could power the sensors in both bright sunlight and dimmer indoor conditions. Moreover, the team found the solar power actually gives the sensors a major power boost that enables greater data transmission distances and the ability to integrate multiple sensors onto a single RFID tag. Depending on certain factors in their environment, such as moisture and heat, the sensors can be left inside or outside for months or potentially years at a time before they degrade enough to require replacement. That can be valuable for any application requiring long-term sensing, indoors and outdoors, including tracking cargo in supply chains, monitoring soil, and monitoring the energy used by equipment in buildings and homes. In recent attempts to create cell-powered sensors, other researchers have used solar cells as energy sources for Internet of Things (IoT) devices. But those are basically shrunken down versions of traditional solar cells, not perovskite. The traditional cells can be efficient, long-lasting, and powerful under certain conditions, but are really infeasible for ubiquitous IoT sensors. Traditional solar cells are bulky and expensive to manufacture, plus they are inflexible and cannot be made transparent, which can be useful for temperature monitoring sensors placed on windows and car windshields. They are also really only designed to efficiently harvest energy from powerful sunlight, not low indoor light. Perovskite cells, on the other hand, can be printed using easy roll-to-roll manufacturing techniques for a few cents each, made thin, flexible, and transparent, and tuned to harvest energy from any kind of indoor and outdoor lighting. The idea then was combining a low-cost power source with the low-cost RFID tags, which are battery-free stickers used to monitor billions of products worldwide. The stickers are equipped with tiny ultra-high frequency antennas that each cost around 3 to 5 cents to make. RFID tags rely on a communication technique called backscatter that transmits data by reflecting modulated wireless signals off the tag and back to a reader. A wireless device called a reader, basically similar to a Wi-Fi router, pings the tag which powers up and backscatters a unique signal containing information about the product it is stuck to. Traditionally, the tags harvest a little of the radio frequency energy sent by the reader to power up a little chip inside that stores data and uses the remaining energy to modulate the returning signal. But that amounts to only a few microwatts of power, which limits their communication range to less than a meter. The MIT researchers' sensor consists of an RFID tag built on a plastic substrate. Directly connected to an integrated circuit on the tag is an array of perovskite solar cells. As with traditional systems, a reader sweeps the room and each tag responds. But instead of using energy from the reader, it draws harvested energy from the perovskite cell to power up its circuit and send data by backscattering RF signals. The key innovations are in the customized cells. They are fabricated in layers with peroxide material sandwiched between an electrode, cathode, and special electron transport layer material. This achieved about 10% efficiency, which is fairly high for still experimental perovskite cells.